So it will becomes mass times delta the extent of mass. So it is true, and it's not that useful because center of mass is not that easy to calculate. It is meaningful because we can easily tell the center of mass velocity for an object, but if you actually want to calculate it, it's kind of hard. So let's stop at this step. If you change the total momentum, then that will equal to the sum of changes of individual momentum inside the system. So if you add all the momentum change of the particles inside your system, that will equal to the total change of the system's momentum. Make sense? Now, what is impulse momentum theorem? What changes momentum of a particle?
Force and time.
Good, and that is called impulse, right? So the change of the first particle's momentum will be the impulse acting on the first particle. Similarly, the change of other particles' momentum will be the impulse acting on it. And adding that up will give you the change of total momentum of the system. Now, when you look at the impulse on the first particle, it comes from external force and internal force. I hope you still remember what is internal force and external force. When you're adding them together, the momentum on the impulse on the first particle will have a part that comes from the external force, and the part that comes from the internal force. And it can be, the internal force may come from a lot of different particles, depends on how many particles is inside the system. But anyway, there's going to be some external force and internal force. For F equals ma, we end up looking at just the external force, and that is helpful because if our system is this card, you don't really know what's the force between the two particles inside the system. You don't really know what's the force between this wheel and the other wheel. But you can know the external force, like the force from my hand on this card. You can usually tell the external force when you are looking at the system. So we want to get rid of its internal force. Now, if you remember what happened here, the internal force cancels when we add all the forces together. Same with here. When we add all the impulse, the internal force, the impulse that is caused by internal forces is just the force times delta t. Impulse is force times how long the time has passed, right? That's why I small f, so you know this is internal force. These are the internal force acting on the first particle, second particle, all the way to the nth particle. Now, there's delta t. Now, if the time difference between initial state and final state I'm looking at is delta t, will the time difference experienced by the first particle the same or different compared to the other particle?
Same.
It's the same, same, right? All the particles will feel the same time difference because time is time. If the first particle says the time has passed for 1 second, all the other particles will agree on the same time difference. So we can take them out of the parentheses. And we just need to add all the internal forces. Then multiply the sum with delta t. Okay? And now, do you guys remember what will the sum of all the internal forces be? In this case, the internal forces is F12 and F21. What is the sum of F12 and F21? It's 0 because it's the interaction between particles. This is going to be equal and opposite according to Newton's third law. So you've done this for F equals ma. It's the same story here. If you add all the internal forces, it's just going to be 0. So you'll see that the contribution of internal impulse or the impulse coming from internal forces will sum up to 0, so you don't need to worry about it. So at the end of the day, the internal forces will cause a net impulse equals to 0. And at the end, you just need to look at the impulse coming from outside of the system. You just need to sum the impulse caused by the external forces